Good evening, everyone. Hope I'm audible. I'm quite glad to be here today in front of you to deliver a session on data labeling through weak supervision and performing a machine learning classification on song lyrics. So today's session is quite an important one, quite a prominent one. The reason is that this in the age of AI, where we are seeing how ChatGPT is revolutionizing everyone and revolutionizing many fields through reinforcement learning through feedback. All right, so the kind of applications that ChatGPT is built upon, actually, the model has trained on large number of huge label data through the contract workers in China and even in African countries, right? Even in India. So there is a lot of data labeling process behind these extraordinary AI systems. So we should not forget about that, right? And the fundamental thing is data labeling. Today's models are quite good, and we can generate good results with modeling. But generating the data labeling and understanding, making labels of the data through heuristic process is what we are going to discuss today. Okay, so let's get started. So this is not semi-supervised learning, Sudhakar. So this is called as a weak supervised learning. So I would demonstrate through for the PPT, and later I would walk you through, if time permits, I will walk you through a Jupyter notebook as well. Okay. So let me share my screen and my presentation also. Can the moderator give me the access to share my screen and also share, start my video as well?
Sir, can you check now?
Okay. So this is my this is our topic today. So what is a weak supervision, right? So we all know that labeling data is not an easy to obtain, right? So we know that a model applied on data plus hardware gives us a machine learning application, right? We do have state-of-the-art models and the hardware, right? We know that GPUs, and we have good CPUs as well, and even the A100 GPUs and TGX servers from NVIDIA. But what we don't have is what it is hard to obtain is label data, right? So obtaining data, training data is expensive, right? And it is not only expensive, it is even time consuming as well, right? So to avoid such expensive and time-consuming things, now we can do a programmatic labeling thing. Okay, in programmatic labeling, I would like to share my video. Can the moderator enable my video? Okay. Okay. So using programmatic labeling, right? So we write some programmatic function and we derive the labels of the data, right? So this is fast, cheap, and dynamic, right? So basically, what is an unstructured data, right? So unstructured data is something which we don't have labels, but we need to structure it, right? So when does that unstructured data gets the structure? So this gets structured when we generate the labels, right? So when we don't have any annotations, it's called as unsupervised learning, right? What we can do is maximum we can do a clustering, segmentation, or we can do a principal component analysis. We can reduce the dimensionality. But our goal is to train the models to make us predict on the future data, right? So here, what we need to do is we have high quality data annotation, right? So we generate it through domain expert, right? These domain expert will generate large annotated data sets, and we can do a supervised learning. But this is too expensive to do, okay? Or these high quality annotations from the domain expert, we first generate a small annotated data set, right? And then we apply a semi-supervised learning. I see some discussion already in the chat happening about semi-supervised learning, right? So then there is a transfer learning approach, right? So this annotation happens through these experts, right? We use it as a test data set, but when we, for example, we have a model that is trained on ImageNet. In case of computer vision, we have a model that's trained on ImageNet. We take the weights, right? And we generate only a small data for our test and gold set of data. And then we apply the transfer learning principle to generate a model that is fine-tuned on our data, right? So that is called as transfer learning. So these three are a common set of approaches, right? But what if in case, right? Here, the thing to important thing is, right? If we have a very high quality annotations, but if we have a very low quality annotations, right? That means these annotations are really not really at a high quality level. That means we are really not sure if this annotation applies in each and every case, right? So this, we are talking about this technique called as a weakly supervised learning, right? So what does that mean? So these are cheap annotations from non-experts. So there is no expert involved. There can be expert, but every time an expert is not needed. So we heuristically identify some patterns. We do batch annotations on clusters of data, right? And using noisy predictions from pre-trained models, we generate a supervised learning large data set. On this supervised learning large data set, right? What we do is we apply our model, right? And we see how good our model is, and we conform with that model. So this is what we are going to do. So how we can generate label data through a low quality annotation. It's not, though it is low quality, our probabilistic model will make them high quality annotations actually, right? So how do we get more label training data, right? So the traditional supervision, right? As you know, we need to generate a lot of training data. So this is too expensive, right? Semi-supervised learning, we just discussed about it. Another one is weak supervision and the transfer learning, right? So for this weak supervision, we get cheaper, low quality labels from non-experts, right? We use no noisy, the labels are a bit noisy because they are definitely not a perfect labels. So, but we, out of this non-perfect, imperfect, noisy labels, we generate a decent labeled data out of it, okay? So how do we do that? So for example, we are a domain expert, or we need not be even domain expert, but we have some idea about the data, okay, and the domain. So here we write some labeled functions, right? So on the unlabeled data, right? These are just Pythonic functions on the label functions, and we generate a label data, right? For example, with this, for example, this is Y is our label, and we are generating. This is called as a generative model, right? So in this generative model, right? So what we are trying to do is, right? That through this generative model, we again applying a discriminative model, right? A noise aware. So this model understands that these labels are noisy labels, and we generate. So this is a final class. So this is a discriminative model. So this is a basically it's called as developed by the researchers from Stanford. This is called a library called Snorkel. So we write our own labeled functions, right? Generative model. We for each observation, right? For each observation, we can have 5 or 6 noisy labels, right? So there is no one set of labels. So through these 5 or 6 noisy labels, this is called generative model. We finally, through the noise over discriminative model, we resolve the labeling data, and we generate one label out of it. On that one label, we generate apply our machine. We train our regular machine learning models, right? So this is what we are going to do. So for example, let's say we are formalizing programmatic labeling, right? For example, we can do a pattern matching. So for example, if there is a pattern matching, we can simply write a regex max as a regex expression, right? Or we can do a topic modeling, right? Or we can do a distant supervision, right? Or we can do any third-party models. We can take, or we can even augment the data. So we can do programmatic labeling, even take our own, write our own functions, or we can use any knowledge aware databases, right? We can take any help of any sources to generate these labels, right? So once we have unlabeled data, right, we have a weak supervision sources. That sources can be anything. You can write your own function, or you can take the help of a database, and based on, you can match this thing to a database and generate a label, right? So you can do anything. Snorkel is a framework, right? A programmatic labeling framework. It generates the probabilistic labels, right? So our goal is to replace this ad hoc weak supervision with a formal, unified, theoretically grounded approach for programmatic labeling. So this is our goal, right? And that will be taken care of by this library, Snorkel. Okay. So for example, there is a library called, let's say we are trying to resolve named entity recognition, right? Everyone does know what is named entity recognition, right? So what we are trying to do here is, let's say we are trying to recognize the St. Francis as a hospital, and this is as a person, right? So if this is the task we are trying to solve here, right? So we are trying to label person versus hospital here. Okay. So now what are the strategies we can use in this case, right? For example, let's say Saint Francis, right? So for example, this is one labeling function, right? This is a simple function, right? Which says that an official classifier, we are saying this as a person. We write another function, right? And this is also coming it as person. But now, right, now we are taking the hospital names. We have an external database where we are matching the Saint Francis is present in that database. Yes, if X is in hospital name, right? If the Saint Francis is in the hospital names database, then we are returning a hospital. So for one set of observation, we are generating 3 labels, right? So though there are either it's a person or hospital, we are generating 3 different labels because we have 3 different functions, right? So these are called noisy. So the sources are noisy, they are conflict, right? This and this gets conflicted, but this and these are correlated. So we out of these 3 noisy labels, right? So finally, we have a pipeline. So we have this labeling function, all right? We have a label model, right? For example, for one label, one observation, we have 4 labels because we have 4 labeling functions. We do a probabilistic training data, right? The Snorkel models and combines the noisy labels into probabilities. And finally, it generates one model where we have one label for each observation, right? So the resulting probabilistic, using the resulting probabilistic labels, we train a model finally, okay? So for this, there is no hand data label is necessary here, okay? So I would take a break here. I would like to take any questions if you have anything. And I'll just checking the chat to see any questions from your side. Okay, I don't see any questions. So, okay, so now I would like to demonstrate this weak supervision on basically song lyrics, right? So we all know we want to scrutinize or we want to filter the objectionable content in the song lyrics, right? So here we have what we are trying to do is Spotify or these kind of or whether the Apple Music or Spotify, all these kind of audio I mean, companies are democratizing the music listening, right? So we can easily listen to the music at anywhere. But how do we how do we scrutinize or filter the objectionable content, right? For example, the lyrics it can have racial slur. The result can have explicit content against religion. The lyrics can have explicit content against against gender or gender discrimination or racial discrimination or anything like that. So, or it can have purely expletive words, right? So how do we filter these kind of, how do we classify, right? When there is a text, a lyric text, how do we classify that this is explicit content? So this is our task here. So for example, there are a lot of songs and there are thousands of songs available publicly. So what we're trying to do is using a gold set of data. We already we've sourced this gold set of labels through our friends and colleague and network. So through using that gold set of data, what we tried to do was that is our test data, but we generated a lot of label data using weak supervision. Okay, so if we just check it, so our goal is to classify the objectionable content in song lyrics as suitable or objectionable. Okay, so and we generated gold label data by crowdsourcing, and we will generate probabilistic labels by weak supervision. Okay, so this is our aim and objectives. So for example, this is our research methodological flow. We have a data and we pre-process the song lyrics, right? And we do the manual labeling of the test set, right? Because that is what we are considering as a gold set of data we did from crowdsourcing, right? And we create and tune the labeling functions, right? I would explain what are those labeling functions in just a while, okay? And we do the label assignment to unlabeled data points, right? We generate probabilistic labels now. And once we generate the labels, we train the regular models such as TF-IDF, Word2Vec, or even any BERT-based models. and we apply on top of it machine learning algorithms for the classification. Right? This is our workflow. Okay. So describing the data, right? So we got this data from open source from the this is the data set is publicly available. So this is our data. So where do we? What is the link? The name of the lyric, right? Whether what is the artist name? What is the genre, right? So this is the basic data what we have, right? So this lyric is something the entire lyric of that song. So our goal is to classify this lyric as either objectionable or suitable, right? So we did some exploratory data analysis. Now you know that when we do that, so you can see that, for example, these kind of word like in hip hop, we can see that words like nigga, right, is more popular, right? So this is actually a racial slur. In popular, it's mostly like love, right? See, feel, way. These are the words. In rock, it's all mostly like love, no, time, and all that stuff. But you can see that hip hop generally has like more racial slur words here. Okay, so now this is our data. Previous slide, please. Maya, what is that exact slide you were looking for? This one?
Hello, sir. Can you repeat?
No, you said slide number 14. Okay. Yeah.
Yeah.
Our goal is to classify the song lyric text into suitable or objectionable by generating these labels. Okay. So where are we here, right? So this is our data. Okay. So we have, right? So we have these many on the training data set. We have 13,544 objectionable entities, right? So this is what this is not like suitable, objectionable. We don't have it. So okay. And on the test data set, we have 929 and the suitable is 2316. So this is the gold set of labeled data, what we have now, right? The rest of the data is not actually labeled. We are going to generate the labels, okay? So here, this is the process of the data labeling. It's not, we generated 12 labeling functions. These are used to vote for each of the data points using the intrinsic rules, okay? Snorkel's libraries pandas LF layer is used to generate label matrix. Then a label model is generated using the label matrix. This label model has been tuned with the validation data set. Then this label model has been used to generate the labels for the unlabeled data points. So this is the workflow for the data labeling. So what are our 12 labeling functions we used? For example, keyword based, right? For example, we check profanity keywords, right? So we already know some profanity words. Using that list of words we checked, and if there are more than 2 words in the text or the song lyric text, we are classifying it as objectionable. Similarly, violent words, sexually explicit words, misogynistic words, drug referencing words, homophobic words, racist words, right? Satanic words or related to some religious words and religious words. So these 9 keyword based, right? So we have a list of words for each of these category. And if the text contains more than 2 or more of these words in the text, we are classifying it as objectionable. If it contains 1, we are unsure of what the classification is. If it doesn't contain any of these words, then we are saying as it's suitable, right? So then we have a third-party based model, right? So we took advantage of TextBob library to calculate subject and polarity. Okay, so here we use these scores to cast a vote and assign a label, right? So here we implemented check subjectivity and check polarity. Okay, and then the third one is rule-based words. Okay, in the rule-based, what we are trying to do is generally we have a function called check subjectivity hip hop. So it works on the assumption that hip hop songs with low subjectivity, right, are often inappropriate, right? So this is a bit controversial, but this is what we felt based on our exploratory data analysis. So altogether, we have 12 labeling functions. So for the 9 keyword-based labeling functions, these are some of the words, right? The profane words consist of these words, right? This is not a complete list. That's why we put etc. here. So for the violent words, these are the words, right? So sexually explicit words, these are the words. So what our labeling function is, as I told you, for profanity, we generate a label. We say that if the text contains any of these words, at least text contains 2 words that are part of this profanity list, then we are classifying this as, we are labeling this as objectionable, right? If it contains only 1 word, we are unsure. If it is 0, we are saying it is suitable. So we generate 3 kind of labels for each labeling function. Okay, so these are some of the words, and once we do the labeling, we generate these labeling functions. We apply the pandas LF layer. We generate a labeling output. Okay, so in this labeling output, it generates basically 4 different categories. Okay, polarity shows which labels each labeling function has emitted when evaluated over a given set of data. Okay, so for example, we either, as I told you, right, each labeling function, we either classify it as suitable, objectionable, or abstain, right? So when we use profane, right, whether it generated both objectionable and suitable, both the classes or both the labels or both the classes or not, right? That is our goal here. If the polarity says 0 and 1, that means this labeling function generated both the labels, right? Coverage means for each labeling function, the coverage metric indicates what fraction of the data the labeling function did not abstain and return one of the values, right? For example, I will show you. Here, the check profanity keywords labeling function, it generated both the classes of the label, okay, 0 and 1. And it covered 96% of the our training data, our samples, right? So that is what coverage means. 4% of the data it is unable to generate, it has abstained. That is what it meant here, okay? And overlap. The overlap metric is a measure of how often 2 labeling functions vote on the same point. Okay, so it indicates like what fraction of the data non-abstain return values from one labeling function have overlapped with non-abstain return values from another labeling function. Okay, so if you just see it here, right, this overlap, right? So for example, here 96% of the it has coverage, right? All of the coverage values here, right, has overlap, right? So that means it's either agreeing, it is agreeing with another labeling function. So that is what it means here. And what about conflict? Conflict is something where it doesn't agree with another labeling function, right? So of the 96%, 95% of the labeling labels, right, we generated on the observation have conflicts. Okay, so that is what this actually meant. Okay, so this is, we generate this on the training data. We generate this on training data. We don't have real labels, right? So this is what we generate here. So for example, if you check religious words only generated only 1 polarity. That means it generated any objectionable, it generated not in the entire data set. This labeling function did not no, not really. The overlap and conflict may not be 1. Okay. So polarity, religious words and subjectivity hip hop are generated only one class. Okay, and you can see that subjectivity hip hop coverage is also very, very low. Okay, so the same labeling function on the testing data, but remember this testing data, we already have generated labels manually, right? Around 3,000 of the songs, we generated the labels manually. On the testing data, if you see, we not only get this data conflict, right, but on the right, so here we can also see that this particular labeling function, if this labeling function applies on our test data, right, on the holdout test data, so here you can see that it is able to classify correctly 962 times. It failed in 2163 times. That means, yeah, I would show it. I will do that when I show you the code. Okay. So here you can see that 30 this labeling function is generating only 30% of the empirical accuracy, right? Whereas the violent keywords is generating 81% of the accuracy on the test data. So the sexually explicit keywords is generating 90% accuracy on the test data, right? So there is no perfect labeling function that achieves a very good results on the test data. Okay. So this is what actually what it went in the testing data. So now what we are going to, this is just accuracy, right? We are just doing the accuracy, and our accuracy might be good because our data is imbalanced data, right? Here we didn't measure any F1 score or anything, so you need not be too much bothered about this empirical accuracy. Okay. So once we have this, what we generated the labels. Once we generated the labels, okay. I would take a short break here. I would like to share you the notebook to show you that. Okay. So hope, are you guys able to see the notebook? Yes. Okay. Cool. So you can see that we have validation, training, and test data set. Okay. So this is the data. So on the training data, we don't have any labeling label function. Right, the training data is not labeled here. You can see that. On the test data, on the validation, right, we have a label here. Similarly, on the test data also, this is training. Yeah, this is validation. Yeah, on the test data also we have a label here, right? 0 or some objectionable or content. Okay, so this is the on the both on the validation and on the test data we have a label, right? We don't have a label on the train data. I hope this is clear to everyone. Okay, so once we have this, once we have the data, so what we are going to do is we are going to generate, as I told you, the labeling functions, right? So what are our labeling functions? So this is some of the pre-processing the data. So this is our labeling function. So from the Snorkel library, we import a labeling function. Okay. Through that labeling function, all right, we are generating a profanity keyword. The first labeling function. So what we are saying is, if there are two items more than or equal to two items, we are classifying that observation, that song lyric as objectionable. If it is in between 0, if it is 1, we are classifying it as abstain because we are not sure. If it is nothing, we are classifying it as suitable, right? So similarly, violent words, we have this list, right? Sexually explicit words, misogynistic words. So these are the labeling functions we use for the entire thing. Satan connotation words, right? So when we say devil, gory, Satan, and all, right? These are positive religious words, right? So that's why here we are saying when there are positive religious words, we are saying if it's greater than or equal to, we are saying suitable, right? We just changed the labeling. Here we are saying if it is greater than 2, we are saying it as objectionable. Here we are saying if it's greater than or equal to 2, here we are saying it's suitable. And because these are positive words, there's nothing wrong in these words here. Similarly, there are negative polarity words and the hip hop thing, right? So we use this. So once we generate these labeling functions, right? So then we apply pandas LF applier. Using this pandas LF applier, right? We put all these labeling functions in a list, and we apply this all the labeling functions on this train and validation data. Okay, that is what we are doing. So when we apply on that validation data, so that is what we get. So now you can see that this is the validation data matrix, right? So this is the first observation. You can see that here it is, we have 12 labeling functions and the 12 outputs, right? Whether the output is yes, we should use it in a context. Yeah, I completely agree with you, David. So that is why that's why these are noisy labels, right? So we are not expert. So if you that context we would get from our modeling aspect, right? So these noisy labels are good enough, right? Let's say with these noisy labels we get an F1 accuracy score of like 0.6 or something. But when we apply a machine learning model, right, we would definitely get a better results that will generate the relationship or the context which we are not which is tough for us to generate a labeling function using context. Okay, the machine learning model will partially take care of that particular aspect. Okay, and when we use models such as when we vectorize the data using BERT or digital BERT, these kind of stuff, our model performance quietly improves. So that also I'm going to demonstrate to you. So if you just see that, right? So this is, you can see that we have all these are 12 labeling functions, right? That's why here, what the first labeling function is saying objectionable, the second label function is saying suitable, third one is saying suitable, the last two are saying abstain, right? So this is what the output what we get. Similarly, on the trained data also, this is what the output we get, right? So if you just see the shape of the data, we have 12 labeling functions, and that's why we have 12 columns here, the 12 outputs, okay? So this is our training data. So this is the polarity, coverage, and conflict, right? So we just discussed. So what is this overlap here? The coverage is 93%. So for profanity, let's say we got 94% coverage. That 94% coverage, right, is overlapping with when you compare with how many, whether this is agreeing with any other, rest of that 11 labels, right? Yes, at least there is entire 94% coverage is agreeing with at least one another labeling function. But is there a conflict? Yes, 92% there is these observations from these labeling functions are conflicted, right? For example, if you can see that here, you can see that this and this are conflict, right? This and this are conflict again, but this and this are what we call as overlap, right? So this is what we went. No, there is nothing called Pearson correlation coefficient here. So this is purely the label we are generating. 1 means objectionable, 0 means suitable, -1 is abstain. Okay, right. See, we are generating, we can see that we are returning suitable, right, objectionable, and abstain. This is what 0, 1. Okay. Yeah, 1 to 1 means overlap, right? You can see that when we are saying this and right, for example, here this and this is called as overlap. Two labeling functions gives the same labeling output, right? This is called overlap, and this is called as conflict. Okay, so that's as simple as that. So once we generate this, right? So now we are going to apply. Now we have 12. So now you can see that we have for each of our observations, or in the train data, we have 61,000 songs, and we have 12 labels, right? This is like, you can say that multi-label data set, right? It's a multi-label data set, right? So, and each label is again either objectionable, suitable, or abstain. So how do we resolve this? So this we are going to resolve using label model. Using a label model, we are going to resolve this. Once we resolve using label model, we have some of the hyperparameters like cardinality is equal to 2. We are going to resolve this, and we are going to generate a probability training data, right? So, for example, you can see here, you can see that 61,030 training data will result in only 2 labels as a I mean, we have no whether it's objectionable or content. Okay, so this is what this label model, right, will does. That probabilistic label model will resolve all the conflicts and overlaps, and it will generate probabilistic labels, right? So you can see that using the label model, you can see that on the label model we have an accuracy of 84% on the validation test, and we have an accuracy on the 85% on the real test data. Okay, both the validation and test data, we have 84 and 85% accuracies. Okay, so this is using the label model. What does this label model do? This label model, we are fitting the label model. Okay, this label model resolves these conflicts, these 12 labels into one label. That is what this label model is doing. Okay, so once we have this label model, okay, so what we can do is, once we have this label model, the rest is going to be straightforward. We will take our train data. Okay, so we can do a count vectorizer method, right? And we can apply a logistic regression on top of it. Okay, and here I will show you the results again one more time. That is to get an indication, right? That is just to see that if how good is our just a label model, right? We are generating, we are resolving the conflict, and we are generating probabilistic label model, right? if we apply the same label model on the test and validation data, how good is our label model? Okay, so basically our machine learning model should be even better than the label model. That is our goal, right? Our machine learning model should be even better than the label model. Okay, so once we have generated the labels, our label model, as I told you, our label model generates the labels, right? You can see that here, right? In the probability train filtered labels, we can see that we have either objectionable or suitable labels, right? So once we have it, we can apply any logistic regression or any model, and we can do that. Okay, I would go back to the PPT, and I would discuss these results with you guys. So, right, once we have the labels resolved, right? So we applied in the beginning, we applied only 3 basic techniques like count vectorizer, TF, IDF, and cloud. Okay, we generated these features from this. This is some of the work has been done long back, even before BERT model has been released. That's why we stuck with the basic models. So these are the features. So, and we applied a very simple algorithm for it, logistic regression, random forest, and SVM. Okay, so when we did that, okay, so these are our results on the test data. Okay, so these are the accuracy results on the test data. But accuracy is not a good metric, as you know, because our data is it is an imbalanced state, so it's not an appropriate measure. Yes, that's why we are using precision recall curves. These are our precision recall curves, and these are our F1 scores. So you can see that we got an F1 score of 0.83 on all these models, right? So it has an accuracy score of, okay, this is an right. So our precision recall scores are at 0.88 and 53. If you see, our recall is at a very low, our recall is not that great, 0.52. So our main goal is to actually improve the recall, but unfortunately our recall is not that great here, right? And our F1 score is at lagging at, all right, our F1 score is at 0.7. So then what we did was, then we applied SMOT on the algorithms because we generated to balance the data, as you guys said, we did the SMOT, and on top of it we applied some latest methods such as debug. Okay, so when we did debug, so this is the improvement we got, right? If you see, earlier our recall was 53, even with any normal algorithm we got our recall of 53. So when we applied SMOT, we got 20% improvement, because that is what you can see the class balancing can do. Okay, and our improvement is more on logistic regression and SVM. We see similar improvement on recall. So we have almost like 20 percentage points jump here, and on F1 measure we got like almost like 10 percentage points jump, right? So this is debug plus logistic regression. The vectorization technique is distill BERT, and the model is logistic regression. But this is debug plus logistic regression on imbalanced data, right? Similarly, this is random forest with SMOT. This is SVM, debug plus SVM with SMOT. Okay. Similarly, these are the TF-IDF plus logistic regression with SMOT compared with only TF-IDF and logistic regression. So you can see that our recall almost everywhere, wherever you see, improved by 20 percentage points. So this way, right? So this way we generated, okay. This way we generated our training. Not only we generated label data, right? We also have a very decent model with a recall of 72% and with an F1 score of like 76%, right? Without any label data. So there is a lot of work that we are planning to do, continue to make the model even better. So we have plans to use CleanLab and other techniques, even to on top of it, we wanted to use a CleanLab. CleanLab is another framework where you can remove the noisy or unreliable labels. So when you remove those labels, our model can even get better. These are some of the techniques what we wanted to apply on the noise generated labels, and then we wanted to use it to further improve our model metrics. Right? So this is about our model. The feature recommendations, right? We can include a speech-to-text framework to identify song lyrics from the audio itself, right? We can apply even more advanced deep learning methods, right? For example, someone is already mentioned, we can use attention-based models and all. So we already used a debug-based with distill BERT technique to vectorize the data, and on top of it, we applied regular machine learning models. But we can even apply advanced algorithms on top of it to make it even better, right? But sometimes I feel like even simple techniques, like for example, balancing the data, can even improve, jump our model metrics a lot. Okay, so this is right. So this is our data. I would like to take, if you have any questions, I would be glad to take it. Snorkel, yeah, okay. You can apply it on images as well. Okay, let me share it. Okay, so I would explain the Snorkel. Right. Shantanu has a question. What is char former based perspective AI? No, I haven't tried what. Okay, Shantanu, let's connect offline, and I would like to know what do you mean by char former based perspective AI. I would definitely like to take a look at it. What we did was we actually, in another technique, we used a one-shot learner as a labeling function. That even gave us good results. Okay. Okay. Thanks, Shantanu. Okay. So this is the Snorkel framework. This is programmatic building training data. Yes, someone has asked a question. Can you do it for images? Yes, there is a method to do it on even image data also. It's not just for text data. You can do it on image data as well, right? So there are a lot of tutorials and transformation things. So I would recommend you guys to go and take a look at it. Let me answer this question. Right. Snorkel for images is already, there is a framework. Right. Yeah. So there's already some papers, and you can apply it on image framework. I never tried it actually. So feel free to go and try and apply it on any image data so can see how it works. And all this data is entire this Snorkel thing is from a group called, if I say from the Stanford team, resources. This is from, yeah, this is from Christopher Reed group, and Alexander Ratner is the one leading this kind of analysis now. And they have even made Snorkel a company, even a startup company also. So you can follow Alexander Ratner. He's quite active on this kind of frameworks, right? So he's the founder and CEO of Snorkel AI, and you can follow some of his papers as well for any of his. And he has written a very excellent thesis. You can check his thesis as well. Any other questions? Shantanu has posted. Okay. I haven't tried Shantanu this thing. Probably we should connect offline to discuss what is this about. Okay. This looks quite interesting paper. Any other questions, guys, before we wind off for today? Like a function, what a score of 0.93 means? Yeah, sure. See, let me explain it from there. Okay. So here, if you see it, right, here on the train data, if you see it, 93% coverage. So what is our train data? 61,030. So we were able to label approximately 90. This is 94%. So we were able to label 94% of the coverage, 94% of the observations of the 61,000 either as 0 or 1. So 6% of the observations have fallen into abstain. Is that clear, Deepak? So for example, if you go back and check the profanity, okay. So in the profanity, we are saying that if there are two words in the song, lyric that fall in this profanity database or profanity words list, right? If there are two words, we are calling it as objectionable. We are saying abstain means we are not very sure. This we are saying giving a -1 if it says one word. If it is 0, we are saying suitable. So this labeling function is able to label only 94, is able to label sure about giving 0 or 1 label to 94% of the observation. So 6% of the observations fall in this abstain category. So that is called as coverage. Okay. Oh, see, it's clear. See, overlap and conflict is straightforward, right? I don't know why it is problematic to you. Just a minute. Yeah. So, what is this? Okay, I'm looking for some Ponnaya commissions. Let's say 10 songs were there, 0 point overlap means that 9 songs are the same from at least. Yes, that's correct. 9 songs had the same output. Okay. 0.9 overlap means 10 songs were labeled by this. Let's say this labeled 94% of the this first one is nothing but the profanity. The second one is the second label function. This third one is the third labeling function. So we have altogether we have 12 labeling functions, right? That's why the shape of this data is 12. Right? There are 12, the outputs of these 12 labeling functions are here. So now, how many labeling functions? So for example, there is one here, right? There is one here, and there is one here, right? So at least there should be one other labeling function which has the same output as this one. Yeah, Abbas, I would upload this notebook. Yeah, sure. I haven't put it in the Git. I would upload this notebook and I would put this in the comments. Okay. Once the video gets uploaded, I will upload this notebook and I will put this in the comments. Okay, so the overlap means this profanity function has an overlap with this another labeling function, but this has also a conflict with this one. Is that clear, Deepak? Right, that is what this means. So this and this is conflict, but again, this and this is overlap. So that is what this means. So you can do, so what you can do on top of it. So what you can do on top of it is, for example, you can remove, since these two have no coverage, you can remove and see if your model improves, right? For example, you can remove only these 3 religious word subjectivity and hip hop. You can remove and see whether this model improves. So we also did one more work, right? So what we did was, this is called as 2-step, right? So the 1 step is, yeah, that's the block you need to follow. So the 1 step is we are generating these labels. And the second thing is we are applying a machine learning model. This is called as a 2-step model. There is also a lot of work has been done on 1-step model where you generate the labels and directly, you not only generate the labels, you apply a model and the model feedback will be incorporated into the labels. Okay, I would share you that paper to you. It's called 1-step, 1-step, 2-step. Yeah, so you can see that escape weak is another weak supervision technique. I just played with it. This is super duper good. So this is escape weak. I would. I don't know why my papers are getting something wrong with my browser. I'm looking into Google Scholar. Yes. So the other one is called Weasel. Weak. Yeah, this is the one I wanted to show you. Okay. I'm looking at Google Scholar. So my internet is very, very slow. Sorry, extremely sorry for that. So this is one of the active field where you would get yeah. So everything is open source these days. So yes, Weasel is the framework. So all right. So this is Yeah. So as I'm telling you, Snorkel is a two-step framework where you generate probabilistic labels. On top of it, you apply a machine learning model. But this is a direct train and evaluate a neural net model, N model from here on. So there is no need to train a separate label model and as anymore as in Snorkel and company. So this is called as one-step method. So I would say I would recommend you guys also to explore this aspect. Okay. So we did some experiment on comparing Weasel versus Snorkel in a different experiment where we derived some aspect-based sentiment analysis, and we got some very good results with respect to this. Weasel gives a slightly superior performance, and it is a bit faster as well. And there is, if you go to Weasel, you can see what are the one-step and two-step methods are there. So probably now, if you guys are in active research, you can look into all these frameworks and methods. Is there any other questions? Okay, I see no other questions, so that would be enough for. Okay, thanks a lot, David. Thanks, Prashant. Feel free to connect with me on LinkedIn. I'm available on LinkedIn, and if anyone is interested in collaborating with me in this work, feel free to collaborate with me. This is my profile, and I do active research on. This is my ResearchGate profile. I do active research on other topics as well, computer vision. My other interest is you can follow my videos on efficient deep learning model in computer vision. So these are my papers on. This is my paper. These are my papers. So recently I gave a talk on efficient neural network approaches for metal casting defection, right? That is my another interesting topic. So how you can compress the neural networks and augmentations, which augmentations work on small and big neural networks, and how to train efficient CNNs. In analytics Vidhya itself, I gave some of the talks. And my other research is all about having an end-to-end model where you can generate label training data as well. Okay. So you can follow me on ResearchGate and feel free to express your interest, and we can collaborate if both of our timings and interest align as well. Okay. And this is my scholar profile. Right, this is my scholar profile, and if you are interested, and we can collaborate. Right. So thanks a lot, and it's great. I really enjoyed this session. Thanks, David, for being so active, and thanks, Deepak, for asking very good questions. I appreciate, yeah, thanks a lot for the opportunity. I really enjoyed giving this talk.